suggestion. Getting the bus service from the airport to Vancouver at 5. Uh, yes, at 5:25 in the evening time. It will be okay for you to drop us there.
Sure. Yeah, sure. Tomorrow or
tomorrow?
Today? Yeah. I'm available.
The time is fine.
Yeah, the time is fine.
Oh, nice. Yeah, so we were actually kind of yeah. I think Raj was sending some email for that, but I'm here at least on Wednesday.
Okay.
So Raj and I were actually hoping to come talk to you guys.
I'll
Let me know. Yeah. And because after 12 or 1 p.m. tomorrow, till about, I think 10 or 12 on Wednesday will be free. But even after that, we have a bit of a meeting.
Sure.
But it'd be great if we can get together.
Absolutely.
That was part of our sort of try to get in touch with the city.
Sounds good.
Okay, that's good. So could you maybe get in touch with Andrew?
Yeah, I'll send a message.
Yeah. So we can start whenever we think we have everyone. You give it a few more minutes. Yeah. I'm glad that I was thinking like standing on my feet for 7 hours today and 5 hours tomorrow is gonna be a bit of a so maybe I'll stand up from time to time and maybe I'll sit for a little bit here. I'll keep it pretty casual. Is Dr. Alam going to come or is he busy?
Just call.
Okay, that's fine.
Yes. Like we have like 15 the one, and from our research groups have like 2. You are here at your LBC party. We can wait for the introduction if you want, or Dr. Abdullah can give the introduction. Okay. Okay, Dr. Thank you.
Wednesday morning will what time? 9. Let me just ask. I think once we're done, put it on there. Yeah. So we have another one at 9:30. Let me see what it says. Would the afternoon work for him after 3? It's like something from 10 to about 3. 9:30 to about 3 on Wednesday. We could meet tomorrow after 12. breakfast or breakfast at 8:30? Are we doing breakfast together? So are we almost full?
Yeah, Pralam was calling me from the parking here, so I
Okay,
saw
well, I
yeah,
can
just,
wait. That's fine.
yeah, I see it.
Thanks for coming.
How are you? See you?
Thanks for coming.
Yeah, no worries.
Thank you all for joining us. We are starting about 15 minutes late. Hopefully by this time everyone is here who intended to. So it's my real pleasure to introduce you to this speaker, Saqib Khan. Many of you might already know him. He is a very renowned bridge engineer in BC. In particularly, he is most known for his specialty in seismic design. He has many years of experiences. Maybe I'll just read out from here. So he is a P.Eng and structural in BC, as well as he is a PE in US, I guess in several states. He has about 20 years of experiences. He has worked with both the private and public sectors on traditional and design build projects. He has gained extensive experience in analysis and design of bridges, inspection and assessment of bridges, and some experience in the assessment of main structures and dams. He has huge experience, obviously, I mentioned about seismic resistant design, retrofit of transit and highway structures, light load assessments, and assessment under fatigue load and other structural deficiencies. And he also serves in the Canadian Highway Bridge Design Code Committee. So today he's going to share his experiences about performance-based design for bridges, particularly for seismic loads. So without further ado, I give the floor to Saqib Khan. Last but not the least, he is currently doing his PhD in our research group. So he is also a PhD student.
I'm one of you.
Yeah. Okay. I guess we have a few people from industry, or yeah. So yeah, and also I see. Okay, great. Thank you. So
Okay.
enjoy.
Thank you, Dr. Alam. So as Dr. Alam mentioned, I'm Saqib Khan. I've been in the industry for about 20 years. Did my master's in structural engineering from UBC Vancouver back in 2001. So I was there for 2 years, 99 to 2001. Hence all the gray you can see. And then I've basically done bridge design and analysis for the last 20 years, starting with my master's thesis. My professor was Bob Sexsmith, who was a very well-known bridge engineer. He taught at Cornell, worked with Buckland and Taylor for many, many years. And when I was at UBC, he was the only person doing a bridge design course at the graduate level, which is something I took, and that's how my interest in bridges started. Then my thesis was about seismic retrofits and about a probability and decision analysis. Since then, I've been in the industry. I've been with the Ministry of Transportation, or I was, for about 3 years. And about a year of that was still seconded out to the consulting industry. So out of the 20 years, I've been with the consulting industry for about 18 plus years. I was inducted into the code committee for Chapter 4 for seismic design back in 2015. So basically, I'm part of the 2019 committee, and the new code is about to come out. It'll hit the market, I think, in November. So we've had lots of good discussions within the code committee about a lot of different things. I will talk about a few things that have hurt us in the last code, in the sense that the design was becoming a little bit on the impractical side. And we've tried to course correct with a few things. There are some ambiguities, and of course we need research to further some of the stuff that's still quite vague in the code. When you look at the steel design, it talks about performance-based design, but it throws you back to S16, which is all force-based design. So there are still some anomalies that we have to deal with. And over the coming 10, 15 years, we hope to streamline things. So 2019 is definitely going to be an improvement. 2014 was a big improvement. Chapter 4 was a complete rewrite as compared to 2006, which again was quite different from 2000, or the 88 code was just, a few pages. So I want to keep it pretty casual, as we're a nice, cozy little group here. My thought is that we go for about 7 hours today, and for about maybe five hours tomorrow, so make it about 12 hours. This is really the gist of a 3-month course I do for the SCABC, the Structural Engineers Association of British Columbia, back in Vancouver. And I do it over 12 weeks. There are 12 lectures, 2 hours each. So I have a lot of material here. Of course, I won't be able to cover everything. I will be touching a little bit on the math side of things, the derivation of things. But I think all you guys being in the university setting are probably going to be quite up on that. A bit of it will be a bit of a revision. And then I think I'll probably take the pulse from the room. I have lots of case studies that I can talk about, the lessons learned when you're doing actual design. How do the code provisions translate into practical design? What are some of the pitfalls you face? What are some of the challenges when you have a site which is very challenging, how do you take those code provisions, how do you take the analysis that is codified and applied in a meaningful manner to an actual problem, which is on a very large scale. It is not a single degree of freedom system or a two-story frame. So we can talk about smaller stuff. I'll talk about components. I will talk about the 4 different types of analysis that are enshrined in the code. But then I want to focus a little bit more on the practical side of things. So just to give you an overview, I'm hoping that this will be a bit of a mix of theory and practice. Hopefully everybody will get something out of it. So are we going to have a break at, I think, every hour and a half or something for 5 minutes, 10 minutes,
Yeah.
kind of? Because the mind will get saturated and my throat is going to get dry. So, okay. So I have about 7 or 8 talks here. I've divided this up. And I wanted to really start with the fundamentals, just to bring your attention to what is the problem, what is the trend that we've seen over the last little bit. How have things evolved and where are things going? What is the context for performance-based design? And why is there this need that has arisen? Because we've been doing force-based design for quite a long time. So I want to talk a little bit about fundamentals. Some of it might be very fundamental stuff. Nevertheless, I want to just touch on it to set the stage. And then I'll talk about the logical design approaches that the code lets us use. And out of that comes this topic, where I'll talk a bit about some of the shortcomings of the force-based design, which sets the stage for performance-based design. That's where the need arises. Then the general framework for performance-based design, capacity design, we all know is very important for any kind of structure which has to take seismic loads. What are some of the analysis techniques? So this is really the overall, the first hour and a half or whatever is going to set the stage, and then we'll get a little bit deeper into some of the things. So when you think about earthquakes, people, a lot of the times we tend to think about a force that's applied to the structure. A much better way to think about it is an applied displacement, because the force you can control as an engineer. That's one thing I really want you to think about, is especially when you're designing a new structure, you are the master of that domain. You can make the structure behave how you want it to behave. When the structure has already been constructed and is found to be deficient, our hands are rather tied. And there are only few things or so many things you can do with it. But when you're dealing with the new structures, you have a much wider playground. So you should not let your analysis and your structure drive your thinking. Your thinking should drive how the structure should behave. So if you take one thing away from this, whether you're going to stay in academia and do some research or you're going to become a consulting engineer, you have to realize that with new structures, with advancements, you can set the direction. Do not let the structure drive you. You drive the structure and its performance. That makes a huge difference. Now, we have the techniques and tools at our hands, but what we see a lot of the times, especially with people with not a lot of experience, is they have something, they put it into the computer, they run the analysis, and they say, it's not working. This is what my numbers are showing me. Okay, now you can do things to the structure to make it behave within the bounds of performance where you think you're going to get that. Okay, so think of an earthquake as a lateral push. And lateral could be longitudinal or transverse. When I use that word for the rest of the 2 days, lateral could be anything. Now, there are, of course, some vertical effects that go with it. But so far, we've been looking at an equivalent force or a base shear. Gets talked about a lot, especially when we look at buildings. We talk about base shear. Not so much in the bridge side of things. We don't really talk about base shear a lot. We're usually talking about an equivalent displacement or a plastic shear force or an elastic shear force. We don't really use the term base shear, although it's the same thing. So we have to realize that when it comes to seismic design, it's usually the substructure and the bends. Now, my talk is focused on bridges, so you'll That's what I'm going to be talking about, not buildings. So the substructure and the bends are the critical elements within a bridge that provide the lateral earthquake resistance. That's where it comes from. The deck over which the traffic rides can be thought of as a rigid diaphragm in building terms. So it just goes for a ride, and those things are usually quite stiff. So when you look at the historic damage in different bridges, you don't see a lot of damage in the girders and the deck. It doesn't happen very often, unless your shear tees are very weak and they break and now things are actually moving. As long as things are tied together and you can transfer the load from the bridge deck into the pier, it's usually the piers and the columns, the cap beams, the foundations that take that damage, because that's where the load is going. So the earthquake lateral load, that's what's imposing the moments and shears into the bridge bend. The cap beam also experiences that load, and so do the columns. This is just a little cartoon which shows us something kind of basic, but it's probably important to just realize what's going on. So this is a typical bridge bend, and let's assume that it's got 5 girders sitting on it. Now you can assume the girder takes a load of tributary area of the deck, brings that load down, so it's got 5 discrete points. So that's just your gravity loading sitting on this bend. And if you look at this, you'll have negative bending over the columns in the cap, goes into positive reverses, and then your these are the bending moment profiles in your columns. And you have some axial load. That's what it's doing under. Now an earthquake comes along, and let's just say that now it's a bidirectional phenomenon, as we all know. It goes this way and that way. But just for simplicity, we can think of it as going this way. So if I have an applied loader and applied displacement this way, this is the bending moment profile or diagram for the cap beam. And below is shown what's happening to the column. And you can see that whereas over here I had negative bending over the column, now it's gone into positive bending. So this is reducing the effect of gravity on this side, or on this side there is negative and negative, so they'll add up. So on the leading side, your cap beam and column moments are increasing. On the axial load side, this will generate some tension, and that will generate some compression. Sorry, that's a typo. So this compression and that compression will add up, and this compression and this tension are going to subtract. So this column gets lighter and that column gets heavier. That's just, I'm big on load paths. You just need to understand in some very simpler terms how things behave. So your gravity and earthquake are now combining in a certain fashion, where bending moments are decreasing and increasing, the axial loads and shears are decreasing and increasing. Okay? And I'll talk about how back in the day they used to miss a lot of this, and we got some bad designs. Not nobody's fault, because we didn't understand the phenomenon back then. But now when we run into those old bridges, we have to go do retrofits on them. Okay, so I want to bring your attention to a couple of important things. Gravity design is primarily strength-based. Okay, so you have your load and you have your capacity. And if your capacity is smaller than your demand, you're basically going to have a failure. And its effect is going to be catastrophic. And we've seen that in buildings where things get overloaded, they collapse. Okay, bridges also have collapsed because the load, the live load that's come onto them has been greater than the demand. Unless there is some way to redistribute that load, it's quite difficult for the structure to sustain that. Because gravity is always there, and it's unidirectional. It's acting downwards, it's always there. Okay, so now if you start to overstress something, it's not like gravity is cycling back and forth. So there is no relief to your system. When we do gravity design, we don't really account for cyclical loading. There's no need to do that. You can do a little bit of load redistribution. You can rely on that. but it's not usually relied on. We do our elastic analysis, we get our elastic demands, there is a disconnect there. Then we do our capacities, which are based on inelastic material properties. Could anyone tell me why that design works or how that design works? So, because there is a disconnect. Our demands are purely based on elastic demands. But when we turn around and we do our capacity, you know, concrete is 0035 or 004 and rebar is yielding. The reason it works is because the elastic envelope is the absolute maximum you'll ever get at any given point in your structure. So if you have the inelastic capacity, when it reaches that, it can just go somewhere else. It will never see a demand more than the elastic demand. So if you have that capacity, your structure is safe. So even though there's a disconnect and we know that, we still design it that way. If you look at ACI or AASHTO, in some circumstances, it'll allow you to redistribute up to 20% from one section to the other, so you can reduce the demand at the ends and increase in the middle or something, but primarily we just rely on elastic. So the big thing here is, if I am unconservative in strength, I overpredict, that can be catastrophic. So if I say my demand is 100 and my capacity is 125, but somehow I've overpredicted, it's not 125, it's 90, I'm in big trouble. My structure is going to really not be in good shape. Now contrast this, and I'll come back to this overprediction, underprediction. The seismic design or analysis is primarily nonlinear. Okay, yes, we do use linear analysis tools, but we have nonlinear time histories or pushovers where we're actually looking at nonlinearities in our structure. We do tend to look at cyclical nature of loading and its effects on strength and stiffness, and we have to look at ductility. We have to rely on load redistribution, and for those of you who've done any kind of pushovers, you know that you're relying on load distribution, redistribution. When one point forms a hinge, you still keep going. The load goes to another point in your system. So here's the thing, with earthquake and analysis and design, over prediction of design strength is not that important than under prediction of over strength capacity. It's a mouthful, but I'll explain that in a minute. Okay, we'll get to this. So imagine in gravity, if you over predict your capacity, that's a no-no. That's a catastrophe. If you over predict in seismic, it's not that big a deal. There is a reason for that. But if you under predict the over strength, then it becomes an issue. And it's tied to, think about it while I talk about other things in your mind, let it percolate. It's got to do with capacity design. I'll give you a hint there. Okay, so we know that a lot of the times we're either using a single mode method or the response spectrum analysis, and those are what? Elastic analysis tools. So how do we then turn around and design for a highly nonlinear phenomenon? So this is where the force-based approach comes from. They have done lots and lots of nonlinear time history analysis on single degree of freedom systems. If you read Chopra, there's a little bit of a description of that in there. And what they've found in a lot of the circumstances is, if you take a system and the earthquake imposes a demand delta on it, so I'm just drawing a force displacement diagram for a linear system. You're going to see that it needs to have a capacity of F elastic to match this earthquake demand. Okay? Now, as I was saying, I can control the system. This might mean a lot of dollars for my bridge or my building. It might make it very expensive. It might make the sizes really, really large. So I say, okay, well, I'm not going to do that because that just means I'm putting big columns and putting in a lot of rebar, and there are other issues with that. I'm only going to design it for this force. Call it Fin elastic. So it goes up here, that's where it yields, and it follows this elastoplastic path. What a lot of the analysis has shown us is this system, which is elastic, and this system, which is elastoplastic, end up at about the same displacement if the initial period is the same. And the period is really a function of the mass and the stiffness, right? So if I take a system which has a 1 second period, and it's going to go here, and then it's going to go plastic and go this way, the same 1 second period, if it has a lot more capacity, it will have to go up there. It'll still end up at the same demand level. So that's what happens if you take these similar triangles and their ratios. You basically come up with the elastic force over the elastic displacement divided by the F2 over delta Y2. You basically find that the R, which is the force reduction factor, right? That's the ratio of this to this. That's the reduction in strength that I'm going to incorporate in my structure. It ends up equal to delta U over delta Y2, which is the ductility in the system. So the penalty I pay is some damage in my system. Now, how do I control that? I have to make sure that it has the ductility to reach the same displacement, but it's not reaching that displacement in an elastic manner. It's going along this plastic branch, which means it's getting some damage in it. So based on this, they've studied different systems, and they've said they have different inherent ductilities. So, you know, a building with a shear wall has an R factor of however much. A single column in a bridge, you can use an R factor of 3. For multiple column bends in a bridge, you can use an R of 5. This is codified in our code right now. So what you do is you run your elastic analysis. You don't change any of the stiffnesses, whatever stiffnesses are there. You run your analysis, whatever you're doing, whether it's single mode or multi-mode response spectrum analysis. Then you go in and you divide your moments by a factor of 3 or 5 or 8, depending on whatever your system is. And you only impart that much capacity to your system. You don't give it the elastic capacity. And then the code says, okay, now we know you've designed it in a way that your strength isn't matching the elastic demand, and your system is going to go along this line. Now you have to control the fact that it doesn't just blow up in your face right here. Everything just goes. So what do you have to do? You have to make sure that you suppress all the non-ductile failure modes. So you've got to put enough reinforcing, you've got to put enough confinement, you've got to make sure your shear failures don't kick in, your foundations are fine, your joints are okay. And if all of that is checked off, then yes, you can get to that point. The code has certain equations, whether it be the building code or the bridge code, that tells you what that rebar or what that detailing needs to look like. Now here is the problem. First, the equal displacement principle only holds true in a loose sense, and it only holds true for sort of longer period structures. So if your structure is 0.2 seconds, it's garbage. It's not going to hold. As soon as it goes ductile, it yields, your R factor is going to go through the roof. And they've done lots of studies, like you can be at around R factor of 20. So if you've designed it for an R factor of 6, guess what? Not going to work. The second thing is, you never go back and explicitly check that your structure is able to display this far. You just have to close your eyes, rely on the code, and say, yeah, with this detailing, I will get this much ductility. Okay, and that can work in some situations. over the course of this this talk, we'll talk about other situations where that's not going to work, and some other issues that are going to come up. Okay, so I'm just going to skip through this because I've basically just described all of this. I was telling Sharif that I have lots of stuff here. I will provide PDFs of everything, and there's probably more that I could talk about for 40 hours here. Of course, I can't do that. But rather than reading, I like to talk and kind of explain that way. Otherwise, people tend to read a bit more. So I would say just listen to me rather than try to read it. But this is basically just describing everything that I've talked about. So I've kind of touched upon this when I say that I'm only going to design to that point. I'm purposely making some part of my structure weaker, right? I'm not going all the way up. So let's talk about that for a second. So here is a typical bridge pent. And for simplicity, I'll just assume that the bases are fixed. Usually you have a foundation, whether it's a spread footing or it's got piles, and soil structure interaction effects do happen, so it's not a fully fixed point. It has some flexibility to it. So if I apply a load to it, and I can go all the way to there, but that means my columns are going to be very large. I'm going to have to stuff a lot of rebar in there. The problem with that is twofold. Here's a typical response spectrum, which we'll talk about in a minute. But this really is just telling you, if your period is so many seconds, it's going to see this much acceleration. You multiply its mass with that acceleration value to get the force. So you can see that as the period of a structure lengthens, the force demand comes down. For periods that are stiff, and the period becomes shorter, the structures that are stiff, you start to climb up this path, right? So now think about this. If I design something that has a period over here, and I cannot make it elastic because that means I'm going to have to increase the sizes, I'm going to have to put more rebar, what is that going to translate into? Yes, but from a mechanics point of view, a larger size and more rebar, what does that translate into? A higher K, very good, right? So when my K is higher, my period is going to be lower. So as I beef up my structure, now I start to climb up this path. So now I might end up here. I might actually make things worse, right? Because now my demand or capacity might actually become worse than what it was before. So just strengthening and making things bigger is not always the way to go. It's a great strategy for gravity loading because gravity is primarily strength driven. So if you're weaker, you increase the size and the strength, you're going to be able to take it. In seismic, you're going to start to chase your tail a lot of the time. So we've got to be pretty careful about this. So I say, okay, no, I'm not going to do that. I'm only going to design it at some point here and then let it do its thing and I'm going to match. So I say, I'm going to make this point a little bit weaker, and this point weaker, and this point weaker, and this point weaker. Okay? So people here have heard of the strong column, weak beam analogy or methodology. That's what we use in buildings. In bridges, we use the opposite. We use the weak column, strong beam methodology. Okay. Can anyone hazard a guess why that might be? Yes. Right. But there is another thing when you look at the buildings, if you make your column the weak link, all of your ductility demands concentrate at the base floor, at the bottom floor. There is no way, because that's where the highest demands are, right? And then it's very, very difficult. So you have to really make them ductile to produce any kind of inelasticity in the upper stories. Okay, so that becomes very difficult. And if you go with beams, now you can spread that plasticity up and down the floors. And now that's a very good mechanism. And you have myriads of beams, so there's a lot of room to redistribute. Whereas in bridges, if you hinge here and hinge here, well, guess what? The whole thing is gonna, under gravity now, it's just gonna come down because it's a mechanism. So we try to form the mechanism in the columns. Now these I would call as fuses. So what does this do? How does this really help us? It helps us by capping this force. Your system can physically not attract more load than this. The earthquake may be a magnitude 9. When these hinges form at magnitude earthquake, let's say spectral acceleration. Let's get away from magnitude. That doesn't mean anything. Let's say that this thing forms hinges, all 4 hinges, and it's a mechanism, and when it becomes a mechanism, it's along this line. Let's say that's 0.4 G. So what happens when an earthquake comes along that puts 0.8 G into it, or tries to put 0.8 G into it? Where would this line go? Move up, move down? What will happen to that line? It will stay exactly where it is, right? Because this is my structural fuse. Contrast that, I want to give you a little analogy to an electrical fuse. There's a slight bit of difference. What does an electrical fuse do? It stops the current from going into the system beyond a certain amperage or voltage. It shuts it down, and it kind of disconnects the current altogether so that your appliance does not malfunction. So here's the difference between an electrical fuse and a structural fuse. We cannot let that happen here. We wanted to get to this point, but then it cannot destroy itself. Because if it has to keep letting this much force go through it, unlike a fuse which just completely shuts down the current. The equivalent analogy here would be that your fuse has now failed, but the consequence of the failure of a structural fuse is your structure falls down. So it gets the force to here, but then it just accumulates the plastic rotations and the plastic displacements, but it lets your structure go back and forth, back and forth. The force will never increase beyond this. So now we, as engineers, have capped the force. Now there's another, not only does this doesn't get transmitted into these columns, what else does it do? It makes capacity design a lot easier. Because now I have to capacity design my beam, my joints, and my foundations relative to this force, and not relative to this force. So my foundation sizes are going to be appropriate. They're going to be lower. The rebar in those are going to be small, but it's going to be less. The shear reinforcement that's going through the columns and the plastic hinges is going to be rather appropriate. My beam reinforcement is going to be rather appropriate. If my columns are putting through 25,000 kilonewton-meters of moment and 15,000 kilonewtons of shear, that's a lot more to deal with than if those are 1/5 of the value that I've just mentioned. Does that make sense? So these structural fuses, as I call them, are basically, in actual parlance, are known as plastic hinges. Probably already know. They have to be confined, and you have to make sure that they can go through a lot of ductility without falling apart. That's how we do good design. Other examples, if you've ever looked at an eccentrically braced frame, there's a link beam in the middle. That's what takes all the inelastic action, and the columns and the beam at the top, that's outside of the link beam in between, is capacity protected. So it's something like that. So it's this beam, that's where all your inelasticity develops. Okay?
So in buildings, we don't, when we have a one-story building, they have two fuses in the beam, but we don't let the columns use it because it's not going to be stable anymore. But in like higher buildings, we do let it. But this one, no, this is unstable. It'll fall.
So yeah, that's a good question, but we don't. That's the thing. Your whole system is just this, right? So this can form 4 hinges. Okay. Now in buildings, you're probably not just going to have one bay. You're going to have multiple bays, even if it is a single-story building. In bridges, you really, per span, you just have those 2 columns. So here, you can have 4 hinges rather than 2.
Isn't this now unstable? It's now we have 4.
Yes, so it is unstable. That's a very good point. The thing is, it is going back and forth.
So we're sure that it'll come back.
Yeah, it comes back, and it might have some residual deformations at the end of the earthquake. That's obviously there. So what we try to do is give it as much ductility as possible, but our fuses are not in the beam because that's taking gravity, and once that happens, it's just going to fall down, right? Because that load never disappears. After an earthquake, this disappears, and if it is not leaning over too far, that P delta would kick in and then make it fall down. It's going to come back. It might have some residual deformations depending on how big the earthquake was.
And does it have to do with the fact that buildings we can't have that much of displacement?
Yeah, with buildings you have the non-structural elements. There's a lot more, from an occupancy point of view. And bridge you can shut down. Buildings you're now evacuating a lot of people. You can have detours to go around the bridge. So it's all of that thinking kind of factors into it. Good point. We can have buckling resistant braces and base isolation bearings that cap that value. So the idea is that we have these structural fuses. They resist up to a maximum of a seismic force, and every other element is stronger than what this force is going to be. Okay, so now when we design these for capacity protection, we don't just design them for this. We have a certain margin on top of this, because that is the problem. Okay? If my shear force here, according or relative to this point, I'm just going to pick a number, is 200 kilonewtons, and my shear capacity is 215 kilonewtons. Think of a scenario where my material is actually stronger than what I've assumed it to be. Instead of my concrete being 30 MPAs, it's 30% more. Let's say it's 40 MPAs. And my rebar, instead of being 400, is say 440, and then we push it, and it goes into strain hardening. Now all of a sudden I'm at 500. What does that mean? That just means that this line is moving up, up, and up, right? So all of a sudden, the actual shear that my structure sees is 250. But guess what's going to happen now? You're going to have a brittle shear failure. So now, under predicting my overstrength demand is a big issue, because I'm trying to capacity protect. So my previous statement should start to make a little bit more sense now. It's the under prediction of the overstrength capacity in the seismic environment that kills you. Now think about under predicting your capacity. So that just means if my hinge was going to form at 1,000 kilonewton meters, it forms at 900 kilonewton meters. So what? that just means my system has to undergo a little bit more plastic deformation. But because it's cycling back and forth, it should be able to absorb that energy in an inelastic manner, right? So gravity, try to not over-predict your basic capacity. That's going to run you in trouble. And seismic, do not under-predict your overstrength, because your overstrength is then going to decide how strong this beam needs to be, how much shear capacity your column and beam need to have, how much your footings need to resist. Okay, once you've done that, you've really safeguarded your structure against a higher level of earthquake. If it can behave in a ductile fashion, it just means it's going to undergo a bit more displacement demand, but as long as the joints aren't going to fail, the foundations aren't going to fail, the shear is not going to kick in as a failure mode, you're going to be okay. And so this is what happens when you don't design for that properly. So you see how far apart, this is an order design. The shear ties, they used to put number 3 bars, which would be, I don't know, 10 Ms or 12 Ms in our parlance, at 12-inch centers, at 300. So number 4, number 3 is at 300 mils. That does not stop your vertical rebar from buckling. It doesn't give you enough shear. It doesn't give enough confinement to the core. Everything that you do for ductile detailing was not present. So this thing has clearly just disintegrated. And these are all elastic designs. So you make something this strong, the earthquake can actually push it here, and it fails right here because it has no way of traveling onto this plastic path. Okay? Now, I want to talk a little bit about the principal shortcomings of the force-based approach. A lot of the times we don't realize that there is an interdependency of strength and stiffness. They are not divorced from each other. They're mutually dependent. And I have a little cartoon that I've just pulled out of Dr. Priestley's book. This is our usual assumption, that I have a system that has a strength M4. Okay, so this is a moment curvature graph. Okay, so as I put more moment into a system, it undergoes more curvature. And here is where it yields, and then it goes plastic. Usually, so this is a bilinearization of it. Really, you have some sort of a post-elastic slope to things. But let's just stick with this. Then I say, okay, I can make this thing stronger so that it doesn't yield at M4, it yields at M3. So for people over here, I've bumped up my capacity. And then to M2 and M1. Now, my assumption basically is that the slope of this line does not change. I'm making something stronger, but I'm not changing its stiffness. That's an incorrect assumption. As you increase the strength of something, the stiffness automatically comes up. Okay, so if I were to take a 914 column and strengthen it with a steel jacket around it for retrofit, and if I anchor that steel jacket into the footing, I have got a composite section, albeit it's about the same size. So I've given it a lot more strength because now concrete and steel are working in unison with each other. It's a composite system. And now it goes from M4 to M1. The system is not this, the system is that. The M4 stiffness is this line, and the M1 stiffness is here. It's usually the yield curvature that stays about the same. I've done lots of studies on those. It's the yield curvature that doesn't change. The strength and stiffness change, whereas with force-based assumption, we have this assumption. Why do I say that? think about that for a second. The other issue is, and this, I think if you take one thing away in terms of the shortcomings of force-based approach, this shows it very, very clearly. So you have a bridge, it's got 3 columns, and they're all different heights. And let's say they're all single column bends. Yeah, I've tried to keep it very, very simple. If I were to design this per the code, I could make a model, a simple, line element model. I run my response spectrum analysis. I get my demands. Okay. The code says if your bends are unicolumn bends, single column bends, you use an R of 3. Okay, fair enough. I go have a look. This column is shorter, it's going to be a lot more stiff. This column is going to be the most flexible, and that column is somewhere in between. So I get these different demands. I divide the demand in each one of them by a factor of 3. Uniformly. That's what I do per the force-based design. This is their own behavior. So now assume that I'm applying an earthquake load on this thing longitudinally. Okay? So because my deck is a very rigid diaphragm, the tops of all these columns are going to see about the same displacement because the deck doesn't compress by 10 inches or 250 mils. It might compress by 2 mils. So let's say that I'm moving this, say 40 mils under this scenario. Just think of the longitudinal push. We won't worry about the transverse for this illustration. If I have a displacement on the system which is sitting here somewhere between C and A, well, guess what? C has already failed. A is way over here, B is over here. So if I draw this thing right here for a bit more clarity, let's say I have an earthquake that puts this much demand on it. In terms of displacement, that's why I keep saying we should think about earthquakes as displacements and not primarily forces, because that makes a big difference. So let's think of one earthquake that's sitting here. With me on this? This thing has yielded. This thing has yielded, but a lot less than this, and this thing is still elastic. What is R? It is a measure of ductility that your system or your column is seeing. Are the 3 columns seeing the same amount of ductility? One is seeing a lot more, one is just beyond this, and one is still elastic. So using an R of 3 means you're using the same amount of ductility for each column. Does that make sense? No. Yet if you were to follow the force-based design, this is exactly what you would do. So when you have large stiffness differences in your system, it really does not capture the behavior appropriately. Any questions on that? Kind of makes sense? Let's think of another system here. Well, this column is already done. These two are way down their plastic path. This R is lower than this R. Okay. Had a question here? So far, if you look at the codes till maybe even 2005 and in the building code right now, and you think back to what happened in Christchurch, our goal has been life safety. Let's keep our buildings standing. They may be completely beaten up. Let's have them standing there. Let's be able to evacuate people out. Well, the public's perception is very different. And the insurance industry works in mysterious ways. So when Christchurch happened and all these buildings that, according to the engineers, performed beautifully, you know, they're leaning 2 degrees or whatever, but hey, we designed them to stay standing. And that was it. They fulfilled their purpose. The design parameters, the design performance was achieved. No doubt about it. But now you're left with something that you have to tear down. And nobody could tell beforehand if this building was going to have repairable damage, or it was going to have some minimal damage, or it was going to be right at collapse, or somewhere in between. Or you or we as engineers cannot explicitly come up with the performance of a structure if we use force-based design, because we never go back and check where each column and the system as a whole actually lies. Okay? It just doesn't work. That framework is simply not there. And therefore, the need for performance-based design arises. And we've, as I was kind of describing to you, we've had this awakening. We've understood the fact that strength is not everything. In fact, what I was describing to you is a clear demonstration that strength without ductility in a seismic environment will be your enemy. It's the wrong thing to do. And I can tell you that over my 20 years, there have been instances where we have gone and cut rebar out of bridge columns. We made them purposefully weaker because then our beams are stronger and we have more ductility in our system. And we've actually cut rebar out as retrofit nightmares. Sounds a bit backwards, but we made sure that live load wise we had enough strength, so gravity wise we were there, but seismically we weakened the systems, because when you weaken the system, you also do what? You make it more flexible. And you start to attract less demand, and you form a plastic hinge earlier, and now you can actually capacity protect things better. So the owners are now increasingly wanting their structures to be serviceable, at least under small and moderate earthquakes. And large earthquakes, you may have a lot of damage, but you want to make sure that nothing falls down. So this is a graphic from this NCHRP Synthesis 440. And you can see that you're going through a whole range of performance. You're fully operational with some hairline cracks. You've got operational level with some wider cracks, but you can go and inject those. Then somewhere in between, there is a fair bit of spalling. You could perhaps go and chip the concrete out, and then either wrap or just put the concrete back on. And out here, you're really just looking at life safety before things start to get into negative stiffness. And finally, you have collapse. There are a couple of examples. This one is complete collapse. And if you were to look at the detailing, I think the failures originated in the joints. The joint shear was just, the capacity was just not there. And this is an example of repairable damage. Now this is well detailed. This is based on Goodnight and others' columns that they've tested in 2012. Good spread of plasticity. You know, you've got cracking that's well spread out, and you can go and inject and do a little bit of other stuff to make it look okay. Okay, so what are the allowable design approaches in our code? We're basically allowed both the force-based design and the performance-based design. The performance-based design is now the de facto methodology. For any complexity, for any seismicity, for any kind of structure, you can use performance-based design. The force-based design we can only use under certain restricted circumstances. And the example I was showing you before, where you have large stiffness differences, the code stops you from using it, because it realizes that now this R factor approach of applying this uniform single R factor to everything just doesn't get you there. And you get these demand concentrations in shorter columns, they destroy themselves, and your structure is rendered either at the verge of collapse or will collapse, or it'll have a lot more damage in certain parts that can't be repaired. Okay, so in our bridge, in our code, we have three bridge categories. We have the lifeline bridges, so think of the Port Mann Bridge, think of the Granville Street Bridge, the big bridges in say, the Metro Vancouver area that if something were to happen, you'd have a lot of economic consequences because of that. Then we have the major route bridges. So, something on Highway 1, something on Highway 97 coming into Kelowna, the underpasses, overpasses, they're the major route. And now if you were to go out into the country or, like smaller bridges that are not economically that important, the code would call them other. Please be mindful that the designation is always assigned to the bridge by the owner. So if it's, say, the City of Vancouver or City of Kelowna or the Ministry of Transportation, they are the ones that decide what importance category they want to give the bridge. The code gives broad guidelines, but it doesn't say the engineer has to come up with it. The idea is for the engineer and the owners to have a conversation, figure out how important something is, what kind of performance they want out of the bridge, and then designate it as within a certain category. And then your performance is tied to it. So things have changed a little bit. So this, again, Port Mann Bridge is lifeline, the Willingdon Avenue interchange. This is on Highway 1. One is carrying Highway 1, and one is just going over Trans-Canada Highway 1. This is in Burnaby, so that's connecting Coquitlam to Vancouver, or sorry, to Surrey. Now the arch span is all gone. So that's, $1 billion plus bridge, so that's a lifeline bridge. This one is a major route structure. So this is how we come up with the seismic performance category, which then tells us what kind of analysis to carry out for our structure. So you have to have your period for the structure and the spectral accelerations for your spectrum, and then you look at whether it's a lifeline bridge or a major route bridge, and you come up with what's called a seismic performance category. It also, and then when you go to the analysis, it depends on whether your bridge is lifeline, major route, or other, and whether it's irregular or regular. So as things become more complicated and more irregular, you have to do a higher level of analysis. So you can see here, now this has changed a little bit in the Ministry of Transportation supplement, and in the next code it's also been incorporated. What we decided as the code committee is, if your bridge is regular, there's no need to do a nonlinear time history analysis, because you can do an elastic dynamic analysis, which is the response spectrum analysis, and you can do the inelastic static pushover analysis, which is the ISPA. Because the bridge is not irregular, we don't expect to see those demand concentrations and irregularities in your system kicking in. And the consensus was that you can then capture the performance appropriately by those two methods. Only if you're in this lifeline irregular category that now you're running the EDA, the ISPA, and the NTHA. So just so that you grasp it, EDA is the elastic dynamic analysis, and that means nothing but the response spectrum analysis, the multimodal. The inelastic static pushover analysis, which is the pushover, and then the nonlinear time history analysis. That's what you do for performance-based design. In performance-based design now, we're looking at 3 different levels of seismicity. So we're looking at 3 different return periods for performance-based design. The one in 475-year return period, the one in 975, and the one in 2475-year return period. So you have to look at all 3, and we have different performance for each one of them.
Yes, I have a question.
Yes.
The irregularity here is in terms of stiffness or
Yes.
geometry?
Yes, it's so it's defined. Say for here, for example, if you have fewer than 7 spans, it's could be so. Even if it is regular in terms of stiffness, if it is more than 7 spans, the code kind of kicks it into the irregular category. Then skew angle has to be less than or equal to 20%. If you have a curved bridge, the arc of that, the angle of that subtended arc, a maximum of 30. Maximum span length ratios for adjacent spans have to stay the same. And then the maximum bend to pier stiffness ratios from span to span also have to remain unchanged. So you can't have one span where the stiffness is 60% of the other one. That's right away going to kick it into an irregular category. Okay, damping we usually use 5%. There is a modification factor, but you can only use it in certain circumstances. This is something I want to point out to you. So these are response spectra for Vancouver and Montreal. This kind of gives us an idea of the seismicity between the two high regions within Canada. What you notice in Vancouver or the west coast of British Columbia is we have a lot of long period energy. So you see how quickly the graph drops in that case. You see the slope of the lines in Montreal. So for very short period structures, say 0.2 to 0.5 seconds, they feel high spectral accelerations. But when you come to Vancouver, you can see that you're not dropping that fast. The slope of the lines is rather gentle. So even with longer periods, there is still energy in our earthquakes. And that's why I've noticed on at least 2 projects in Montreal that on bridges, you're usually over 0.5 seconds. Short span, 0.67, and as you're getting longer, you're getting into a second range or whatever. It's the non-seismic loads that start to govern. The seismic doesn't govern. Whereas in Vancouver, it almost never happens. Vancouver or Victoria, the non-seismic lateral loads like wind or ice or something else would govern. It's almost always seismic. You can also see here, on average, our long period ordinates in Vancouver versus Montreal are about 4.5 times higher. Okay. If you look at the Vancouver ordinates themselves, the short to long period ratio is about 11. So when you look at this versus long period, you're looking at a factor of 11, whereas in Montreal, you're looking at a factor of 33, which clearly shows that there's a lot more short period energy, and then it drops off pretty quickly. So if you're designing in Eastern Canada in that pocket, be wary if your structure has really short period. I'm not saying that when it's a long period structure that you just throw it out, you do your checks, but you'll most probably find that it doesn't go. Okay, this is just giving you a snapshot of how things have changed from S606 to S614. In S606, our basic period was 475 unit return. Now we are dealing with 2475. And in this code now for the force-based design, we only look at 2475 unit return period. We don't look at the other 2. We look at all 3 for performance-based, but we only look at 2475 for force-based, and that's what you apply the R factors to. There is still an importance factor in the force-based design, so it bumps up the values for your spectrum by a factor of 1.5. So for other bridges, you have a factor of 1, so using your baseline response spectrum. For major root bridges, if you're doing force-based design, you have to increase it by 50%. Still use the same R. For lifeline bridges, force-based design is not allowed. You have to do performance-based design. And when you're doing performance-based design, because we're looking at 3 different levels, there is no concept of an importance factor. Because you're already looking at 3 different distinct seismicities. So keep that in mind. We also have to look at some vertical effects in the code, especially if you're in close proximity of active faults, where you get near fault effects within 10 kilometers. So the vertical spectrum can be generated usually here in British Columbia, we're a bit spoiled. We always get a geotechnical engineer, which to me is the right thing to do. Not make the structurals make wrong decisions for coming up with this sort of stuff. So you can do site-specific analysis. Now, when you do site-specific analysis and you come up with your vertical spectrum, it cannot be lower than half of your horizontal values. And if you don't have that, you can just use 2/3 of your horizontal spectrum as your vertical spectrum if you have no site-specific conditions. This I've already described. So these are some of the code R values. So water type piers, you're looking at 2. Single columns, you're looking at 4. For multi-column bends, you're looking at 5. You can also think of a bent which has 2 columns versus a bent which has 7 columns. I don't know how much using the same R value makes sense, because one system has less redundancy, the other system has a lot more redundancy. A lot more plastic hinges can be formed. A lot more load redistribution can happen. Force-based design tends to miss those finer points. This is where the code started. It said, so now this is coming to performance side of things. As I was mentioning, for performance-based design, you have to look at all 3 levels. And then you have concomitant damage states that you have to satisfy. So for 475, let's just look at lifeline bridges. And it says immediate service with no damage, then immediate service with minimal damage, and limited service with repairable damage. The issue was that the code has no description of none. It never defined it anywhere. So it was a little bit of an issue. And when you looked at minimal, you could really see that it was minimal damage. Like, you can't have an earthquake and not have some concrete cracking. It just doesn't happen unless it's a 50-year return and you've designed it for a 2,500-year return period event. So the practice was to basically just use 5% and minimal and 2475 and repairable. And that's what the new code is going to, that none and immediate, they've been taken out. Okay. Minimal just didn't mean anything, and I can go on about that for a while. But this is something I want to talk about for a minute here. When you looked at the description of minimal damage, the concrete strain was restricted to 0.004, and the steel strain was restricted to 0.002. So let's stick with that. So let's say you're running a 475-year return period earthquake, and your capacity has to be based on your, say you're designing a column, it gets a certain moment. Its capacity, when you design its capacity, has to be such that the number you pick has to have strain values lower than those, both of those. So the concrete cannot reach 0.004 or can only just reach 0.004, and the rebar can only yield up to 0.002, just touch yielding. Now I want to invite everyone to think about this for maybe 10 seconds and think of a problem with that. Do those strain limits scream something at you? So they have to be simultaneously satisfied, as in, I shouldn't say simultaneously satisfied, it's the lower of the two. So if your steel gets to 0.0022, while your concrete is at 0.003, you haven't met the performance, right? Because it's the more stringent of the two. Neither one of them can be violated. So with that pair, does that ring a bell?
Very large reinforcement ratio.
Right, but why?
Because if you need to maintain that value, like give that the slope is the same, you want to reach the yielding strain of 0.002, the concrete strain will be higher, If you want to maintain the same concrete strain, the strain in the steel will be very
Right.
low. So you have
So
to
that's a very good point. That's a good description of it. There is a philosophical issue with it. Is what I want to hear. If anybody can catch on to that, there's a philosophical issue, and one of Dr. Alam's P.Eng, he did his master's on this whole thing basically, and we you can see that it creates problems, and yeah, you end up with 6% rebar in the column.
Yes.
But I'm driving at a very fundamental issue. Think about gravity design and think about reinforced concrete design, and think back to your third year or second year, whenever you took it. What is the failure mode that is preferred? So if I tell you three things: primary tension failure, balanced failure, and primary compression failure, which one are we told throughout our lives, starting at reinforced concrete 1, is the preferred failure mode in a reinforced concrete section? Primary tension failure. What is this doing? It's not letting you reach yielding when concrete hits 004. So if you've done any PM interaction in your life ever, you know that the codes don't let you stuff so much rebar into it that your steel hasn't yielded while your concrete has reached 0035 or 004. Why? Because it doesn't give you any visual warning. It just concrete compresses, goes through compression failure, and it gives rise to a brittle failure mode. So now in order to, or the goal was noble. I don't have a problem with that. The goal was, let's try and keep the damage to a minimum. And let's not let our rebar yield at all. Well, so then what happens is you end up with 6% rebar. Think about the ramifications of that, the repercussions. What happens to capacity design? Can you capacity protect your foundation against a column that has 6% rebar? Has anyone worked on site and asked a contractor to put 6% rebar in a column? Never gonna happen. You'll get a beating at site. Never gonna happen. So we've had lots of fruitful discussions and lots of internal debate, and finally there is consensus that this is highly restrictive and that we cannot design to this. The funny thing is, for Montreal, it doesn't matter so much because your non-seismic loads govern, and when you put that much rebar in at whatever 1% or 2%, your nominal capacity is much higher than your earthquake demand, so you are not yielding. That's fine, but in British Columbia, the West Coast, it's a big problem. Okay, so now there is going to be uniformity across the board. By the way, nobody could ever design to this. I've had to fight battles on the Evergreen line, which was that happened before this code came out, but the rebar strains were even more strict for the higher levels, and this was one of them. And I had to plead in front of a seismic panel of experts and kind of bring them on board and get the project specific criteria changed because we just simply could not design this. Okay, so then now this 002 has gone to 01, so it's 5 times. So it's putting you on the yield plateau. But if you look at Dr. Priestley's book, and then so that's the one from 98. If you look at the one from 2007, you will find values for minimal damage of 0.01 to 0.015. And the idea there is that you'll have some hairline cracking. You can inject a little bit of grout, or if you're so worried about the aesthetics or whatever. But also from a durability point of view, you don't want water ingress and all that. So do a little bit of grouting. I think your crack widths are less than 1 mil at that point for those kind of strains. It's an earthquake event. Even under gravity, if you had an overload, you would want to see some rebar yielding. You would not want to have the concrete crushing. Okay, then it has all these other things. You got to have your 4 dead plus 50 live, 50% live load carrying capacity. This is a typo, please, so when you get to it. This is actually looking at extensive damage. That's why you see the rebars are much higher. And then comes my most, most favorite bullet point. 90% seismic capacity retention for aftershocks for repairable damage. What else? For extensive damage, 80% seismic capacity retention for aftershocks. And we had lots of discussions over several years with the Ministry of Transportation, within the Code Committee. And the big thing here was, okay, you guys, we've stuck that in. What does this mean? What do we mean by 80% retention, 90% retention? Is it force retention? Is it displacement retention? Is it stiffness degradation? What are we driving at here? Nobody really had the answer. The whole idea, I understand, the idea was to not push your system so far that an aftershock comes along and you're so far down that degraded path, down that negative slope, negative stiffness, that now you're going to be on the ground. Okay, so they wanted to give the system some sort of capacity that's left in there to take care of it. But it's very ambiguous. And really that's what I'm doing for my PhD, is see what we can come up with in the next 4 or 5 years. But I'll come back to that. I've put one interpretation on it, that is, while things are happening, in the meanwhile, the design engineers or the students, if you were to satisfy that, how you would do it using a simple pushover analysis. Okay, I want to just give you a quick flavor of how things have evolved. So this is the Portman Highway 1 project, which again predates the code. You look at this is the main bridge performance criteria lifeline structure for the Portman. And here, if you look at the service, it's got possible loss of service, significant damage, no collapse. If you look at the new code, you would be designing it to a higher level. You'd be designing it to limited service and repairable damage, not significant damage. So the bar has come up a little bit. These were the strain limits back then, and you can see for minimal damage, the strain limit is 0.1. The new code took it back to 0.02, became quite difficult. For the significant damage, you're sitting at concrete crushing is not allowed, which means you could take it to 100%. Now that's been scaled back to what this is, and a steel rebar of 0.05, a steel rebar strain of 0.05. Here it was 75% of the ultimate. This is the evergreen line, which hopefully tomorrow I can talk about and give you a bit of a case study. Here we had 4 different return periods, but not all of them were applicable to different zones of the evergreen line. So this is an extension to the Millennium Line SkyTrain station in Metroban. So there's 100-year, 475, 975, and subduction. This was really applied to portions of the evergreen line where we didn't have huge liquefaction issues. Whereas everywhere there were liquefaction issues, we had this performance, and it was a little bit backwards for me, because here you see with no liquefaction at 975, you're targeting life safety or no collapse. There's no liquefaction, it's easier to design, and you're designing to a level of no collapse. Well, now you're in ground that's moving 2 meters, and all of a sudden you've got to design it to repair damage. It was quite a challenge. But we made it work. And for subduction, it was repairable. So here, 475 was repairable for the areas where there was no liquefaction, but we had repairable for liquefaction areas under 975. 100 years was immediate use, so it was the code now is using 475 for immediate use. Was that okay with that criteria? The ministry for the evergreen line, yeah, it was a ministry criteria, which again we had to talked to them about quite a bit, but it was really through the material strains. What was really hurting us was the 0.002s and all of those that we couldn't design. Once we got that to a reasonable point, it became a lot easier. And then for liquefaction, we got permission to allow some plastic hinging within the ground on our piles, because we just could not design them when the soil was moving so much. Okay, so I'm setting the stage. Don't get lost. This all will come together because I'm giving you sort of the high level, and then we'll go into the nuts and bolts of everything. Now, how do we show performance compliance? Okay, so it's basically, in our code, it's basically through material strains. You'll see some documents where you're looking at plastic rotations. You're looking at other things, but in our code, it's primarily strain-based, material strain-based. So you're going all the way down. You're going below plastic strains. You're not saying, oh, my plastic strain is 0.01 radians, and therefore I've met the target. We're going beyond that. As a minimum, you have to do an elastic, static, or dynamic analysis, and you have to do a pushover. Because without a pushover, you cannot get to rotations, strains, curvatures. None of that comes out of a response spectrum analysis. So to show performance compliance, which is based on material strains, this is the minimum you have to do. Aftershock compliance would be best demonstrated by nonlinear time history analysis, but I don't think anybody has done that so far. Like I said, I came up with one interpretation of the clauses, which I'll share with you, and we'll see what comes out of that. Okay, so these are the 4 analysis techniques. Now we can start to get a little bit into the nuts and bolts and some of the issues and how the derivations come about. So it'll get a bit more theoretical at times. I'm going to try and stay away from that as much as possible, because I know you guys, you all probably read Chopra and the derivations are all there, but I will provide all of that stuff. So in the code, the elastic static analysis, again, this is quasi-static, right? This is the uniform load method and the single mode method. And those you really use for bridges that you think are going to behave in the first mode, because that's what it's capturing. Whether it's the single mode method or the uniform load method, it captures the first longitudinal mode and the first transverse mode. It doesn't go beyond that. So if you think you've got a 3-span bridge with 2 columns each, and it's straight and there are no skews, and now it's going to have more than 90% of mass participation this way and 90% of mass participation that way. In the first mode, you can use those. Then we have the elastic dynamic analysis, which is the multimodal response spectrum analysis, which is, if you have long bridges and you have some sort of, not exactly the same thing, and you have a continuous deck, for example, then you need to go to that to capture 90% of modal mass, which I think you would know. Buildings and bridges, they all want you to do that. In elastic static pushover analysis, which I'll just start calling pushover analysis now, or ISPA, you have to do a moment curvature analysis that gets in there as an input. And the question always is, how far are you going to push? Because we can keep pushing, but what's a meaningful displacement that you want to put into your system? And then we'll also talk about the nonlinear time history analysis. There you can use the direct integration of your equation of motion or equations of motion. And if you have only a few degrees of freedom where you're going to have concentrated plasticity, for example, if you put base isolation bearings, and they're the only ones that are going to yield and go nonlinear, then there is a fast nonlinear analysis, which is, it's a contradiction in terms, but it's a nonlinear modal analysis. You use Ritz vectors for that, and I've used that once or twice using CSI Bridge. It speeds up things a lot more. We'll just touch on some of those things. Damping is a big question mark. There is still a lot of discussion happening in the academia and also in the design office. You're always wondering how best to model damping, how not to over damp your system, how not to under damp it so that you end up in numerical instabilities, all of that. Okay, so when we run our response spectrum analysis or modal analysis, we do not want to use uncracked stiffness of concrete. It doesn't help us, because if I were to draw let's finish this and then we'll take a break. This is usually what happens in reinforced concrete. If I were to draw the moment curvature diagram, your cracking happens really early on. This concrete cracks at approximately 0.4 root f prime c, in MPa units. So it cracks right there, and there's a big difference between this slope and this slope. And then your first rebar yields, and then you have subsequent yielding, and then you have some post-elastic slope to it. When we model, we do not want to model your structure even though you're using elastic analysis. You don't want to model this, because what we want to get out of it is the displacement. Okay, so we want to use an effective stiffness that kind of goes through the first yield point. That's the stiffness we want to use, and we call it effective stiffness. And that can be anywhere from 30 to 50% of your gross stiffness. Okay, now how do we do that? If you run your moment curvature analysis, you can see this is where you're cracking. And if you were to go along that first line, you would go through here, that green line, which is not correct. Okay, so you go through this initial yielding, and you calculate the slope of this line to account for the fact that when you're looking at the effective stiffness of concrete, it's going to be much smaller. The other thing that happens is when you're using soil springs for your soil structure interaction, your soil springs are also nonlinear. So they stay linear to a certain point, and then they go nonlinear. So what you have to do is, when you're using your response spectrum analysis, you cannot use the initial stiffness. You have to use one stiffness, go back, look at it, and see if the force is up here, you know that stiffness is wrong. So you come back and you recorrect until you converge. So it becomes a little bit tedious. But in response spectrum analysis, you have to get that secant stiffness. So think about two things. One is the effective stiffness of concrete, and when you have the soil springs, you have to figure that out, because the program on its own can't. It's a linear analysis, so you only are allowed to put in one stiffness. And so you go and you look at the spring displacement and force, and if you find that it's off the chart, off the graph, then you have to correct it in a bit of a, so you keep correcting it till you find that converged secant stiffness, and then you come up with your lower displacements out of that model. We'll talk more about these things. We'll talk about combinations afterwards. Pushover analysis we'll talk about. I'll show you certain things. Of course, nonlinear time history analysis. How many? How do you match? How does damping work? All of that. All of this is coming up, so I'm just skipping through here. I understand this is an hour and 45 minutes. We need to take a bit of a break. This is probably the last thing I want to talk to you about. As you develop a plastic hinge and you cycle it back and forth, the concrete aggregate interlock starts to degrade. Okay, so the concrete shear capacity, within a concrete reinforced concrete section, your shear capacity comes out of two things, right? One is the concrete, V sub C, and one is steel, V sub S. V sub S doesn't degrade unless you haven't properly detailed your hooks into the core or your spiral is continuous and properly wound. If that happens, if you're like this and the covers falls off, it opens up, now all your steel is gone. But let's assume that you detailed it properly. There is still a problem. The problem is that as you form a plastic hinge and you cycle it back and forth, you are going to have mechanisms kicking in where the concrete aggregate bond starts to get lost. So your V sub C starts to come down. And this is a figure from Dr. Priestley's book, and it shows the problem, the issue. Okay, so and it kind of goes back to what I was talking about in terms of having a system that's too stiff and too strong. So let's say you have a system that's really strong, and that's system number 1. It can go up that line. Okay, and here is my shear capacity envelope, this dashed line. Okay, so you see what's happening. Up to a curvature of about 3, this line is straight, which means there is no degradation. Your shear capacity is all of it. When you go beyond that, it starts to drop, it starts to come down, and then it levels off at some point. So it's fully degraded in terms of the concrete shear capacity. Now think of this system number 1. It wants to go up to here, up to V1, and go there. Well, what's going to happen? When the base shear hits this point, the system is going to fail because it doesn't have the shear capacity relative to the peak force that it can attain. So if you made it so strong that it can generate a lot of bending moment, which is accompanied by a higher shear force, it's not helping you. System number 2, on the other hand, yields here, but then it's got some post-elastic stiffness. Now it starts to keep climbing up, but it's generating a lot of ductility now, right? Which means what's happening in your plastic hinges? They are degrading. So the shear capacity envelope is coming down. So in theory, this system can go all the way up to there, but it clips the shear envelope right there. So for this system, you're going to have a shear failure at this point. The third one is a system which is nice, it is ductile, it's not that strong, its flexural ductility is all the way out to here, which is about the same as these guys, but it never is going to clip that envelope. So which system do you think we should design for? Number 3, it gives you all the ductility. It gives you, so this ductility means it's giving you the same amount of displacement, but it's not going to run into shear issues. And when that happens, especially on shorter things, shorter columns, you run into problems. Okay, so let's just quickly talk about a couple of takeaways and we'll wrap it up. So several changes were brought into S16. This is a major rewrite. The whole chapter got rewritten basically. S619, we have a few more changes, things that we've learned over the last 5 years from 2014 to now. Of course, FBD and PBD are both incorporated. PBD can be used for any bridge. FBD is subject to previous preconditions, right? So for any lifeline bridge, no. For major root and other structures, yes, as long as they're somewhat regular. Okay? Back in the day, our anchor return period were 475 for force-based design. Now it's 2475, and we're using 3 return periods: 475, 975, 2475 for our performance-based design. Now, it's true that there is more analytical effort when you're doing things based on performance-based design relative to force-based design, because you're running one analysis, you're using an R value, you're not doing any pushovers, you're not doing any of that, you're not doing any nonlinear time histories, but the effort is worth it. Owners are asking for it, the society is asking for it. It's time that we start to think about displacements, strains, rotations, material and also system performance. And don't just close our eyes and say, oh, it's an R of 3, when reality is this. An R of 3 is not correct. An R of 3 I'm just using as an example. As a minimum, you'll have to run some sort of a linear analysis for demands with effective stiffnesses and a pushover analysis to come up with your strains and rotations. So S614 criteria are a bit more stringent as compared to S606 in some of the previous BC projects. They became too stringent on the base level, the 475. They moved away from that a little bit. I think we have hit the right target strain values. Because before we couldn't really show that rebar strain below yield was feasible for minimal or no damage. So for owners and design engineers and even students, when you're doing your research, you gotta be a little bit mindful about the fact that there is more analytical effort, but it gives you a much better and deeper understanding of your structure, of your research project, of your actual design, rather than just saying, oh, I'm using an R of this, and then I'm just putting my ties at this interval and hooking them into the core. Okay, thank God.
So we will start at 11?
Yeah, 11 is fine. Sure, we can quickly, I need some water.
باش ايش هو
شفت من الشباب يا اخي
فاضي ده فاضي
بس انت حولت يا باشا شو حولت؟
ما هو فاضي انت عايز ايه ده فاضي
لا ما انت حولت يا باشا
يا عم مفيش حاجه بسيطه شو كانوا عايزين يقول لك هديه وبعدين قلنا مش عارفين ايه اللي انت عايزك ممكن نجيب حاجه ما تعجبكش فقلنا بقى ما نجيب لك هديه نجيب وانت تجيب هديه جيب بيهم انت الهديه I need to, I'm not sure we have to. I just waiting for them at 11. No, I just have to order pizza at lunch. They didn't, yeah, they didn't mention anything about coffee.
Okay.
When you came back, they came.
I'm making Qatar.